Hello, everyone, and welcome to Toronto Machine Learning Marco Summit in Healthcare. I'm Beta, a data scientist at Deloitte, and your host for this talk. I have a great privilege to welcoming Frank Rudzicz, who's gonna leading us through a very interesting talk about some risk of deep machine learning, mitigation of those risks, and the potential of deep machine learning in the operating room. Frank is a scientist at the Shing Knowledge Institute at Unity Health Toronto. He is Director of Artificial Intelligence at Surgical Safety Technologies and Associate Professor of Computer Science at the University of Toronto, co-founder of WinterLight Labs, faculty member at the Vector Institute for Artificial Intelligence, and CIFAR Chair in Artificial Intelligence. His work is in machine learning in healthcare, especially in natural language processing, speech recognition, and surgical safety. His research has appeared in popular media such as Scientific American, CBC, Globe and Mail, and in scientific press such as Nature. Before starting, I just want to mention, if you have any questions, feel free to post them in the chat section. I'll make sure to collect your question and we discuss them at the end of the talk. Without further ado, back to you, Frank.
Hi, thank you for that introduction. It's a pleasure to be virtually here. I just want to also say how important the TMLS organization is to our community. So it's a great honor to be able to speak to you about some of our work here today. So some of my conflicts of interest I have to disclose have already been mentioned. We'll be talking about aspects related to machine learning in healthcare, which connects to one of the companies I founded called WinterLight Labs. But more specifically, the main conflict of interest today is between my research at Vector and the University of Toronto and my Director of AI position at Surgical Safety Technologies, which I'll talk a bit about today. So generally, I have a short amount of time to cover aspects related to surgery, technology, and ethics. So it's going to be a bit superficial, but I hope we can cover enough topics today. Oh yeah, so we will be showing some examples of our systems in practice. And because we're dealing with technology within the operating room, there's going to be images which might be disturbing to some. There's going to be images of blood. They might be blurry because of the encoding virtually, but just be warned, if you're squeamish, you might want to leave in the next 3 seconds. Okay, great. So at the Surgical Safety Technologies, we've developed a product called the OR Black Box, which is really a collection of technologies that work together. There's no actual box that's black. It's really sensors put into place in and around the operating room, and the computational and human capacity outside of the operating room that processes all this data that we collect. So the types of sensors we have include wall-mounted video cameras. Usually there's about 4, like one on every wall of the operating room. Microphones, like directional microphones that can zoom in and listen to individuals speaking. We've done some work with wearable technologies, but typically the main source of raw input is either endoscopic cameras or laparoscopic cameras. These are cameras that are inserted into the body during surgery that allows a surgeon to really see what's going on. We also have direct access to patient physiology, environmental factors, and other devices. So in particular, we're getting a lot of structured information from the medical record, as well as some textual data. So we have access to some of the clinical notes that are associated with some of these cases. And after we collect all of this data, we can do a variety of things. So we assess for various kinds of risks and hazards. Is there risky behavior by any of the operating team? We want to be able to analyze, for safety threats, to see how people in the team have overcome those threats and have demonstrated resilience. We're interested in assessing for surgical team performance. So what that essentially means is, I'll get back to this in a moment, but during an operation, can you evaluate objectively how technically skilled the surgeon actually is? And this is important, obviously, as it relates to adverse events in the operating room, but also within the context of education. Is this a young learner who's learning how to go through particular surgical procedures? We're also interested in assessing for surgical technologies. So occasionally we work with various kinds of companies. They want to evaluate whether their stapler is more effective or safer than that of their competitors. So we can really obtain a lot of deep objective data through these systems. We're interested in assessing for efficiency and so on. This only scratches the surface of what we're really capable of doing and what we've kind of looked at doing. But these are sort of the kinds of, just to give you a flavor of the kinds of outputs we get from the black box. In all of these cases, I mean, we're not just arbitrarily putting together sensors and arbitrarily looking for potential tasks that provide us a signal for machine learning or otherwise. Really, all of these tasks we're trying to solve are really driven by the clinicians, and fundamentally we want to save lives at the end of the day. So everything's kind of driven from these high-level goals. So I just want to mention a little bit of what we can do with video cameras. One of the most fundamental tasks we do from the wall-mounted cameras is to track the individuals within the scene. So you can see here a kind of rudimentary skeletonization of individuals in the room. And then you can, given more than one, or even these days one camera, you can get a really good three-dimensional representation of the room, how close are people to each other. We've actually used this technology very briefly to look for breaks in sterility during COVID. So, with a 3D representation, you can tell whether a nurse or a staff have interacted with a device, after breaking sterility, for example. That's kind of important. Also, with these kind of global room metrics, we're able to listen to conversations or listen to sounds in the OR. That's actually super important. We've used sounds to look for issues related to distractions. We've looked at speech in the context of non-technical skills and communication. Can you detect breakdowns in communication, power dynamics, and so on? So there's like, the sky's the limit in terms of what we're able to do with some of these data. And speaking of tracking people, and the reason why this is one of the most fundamental tasks for the OR black box is that if we're going to be analyzing these data and providing back snippets of these data to customers, we really need to make sure that the data is de-identified. So this is a sim center. This is not a real surgery, but these are real surgeons. So we have a relatively straightforward segmentation algorithm that detects people in the room. Other instruments applies a relatively simple filter. This is an old version. This is several months old. We've made some improvements since there, but we do a deeper blurring of the face, less blurring around the bodies. A lot of the clinicians we've spoken to are very keen on looking at the fine detail in the room. They want to know exactly what the hands are doing, which way people are looking in the rooms. We can't de-identify completely and still maintain clinical relevance. So there's a bit of compromise between what is relevant to the clinicians and what we're capable of doing with modern de-identification. But as long as we make it so that we can re-identify somebody using the video and associated data, we're happy. Now, we actually have a new product we just launched a few weeks ago. This is already being deployed across North America. It's called Black Box Explorer. It's kind of a stripped down version of the full OR black box, in which we don't have necessarily wall-mounted cameras and microphones, but we're focusing mostly on just like the internal view videos and some of the structured data we get from medical records. So in this case, some subset of the sensors are recording 24 hours a day, 7 days a week, potentially. Surgeons come into the room, they sign in using our NFC technology. They enter a little bit of information about the surgery, if it's not already in the medical record, and then we gather data directly from the operating room to our secured cloud. We can also support, uploading video files after the fact, but we're interested in doing real-time live video recording with Black Box Explorer. And then what we get once we collect all this data is, at the first pass, a kind of a video library, a YouTube for surgery, in which all of the surgeries performed by an individual can be arranged in like a YouTube-like library, like the one shown here. We're going to be integrating a lot of features that I don't really have time to get into right now. But part of this involves, sharing data amongst your colleagues in a team. One of the cool things about this is that when data is uploaded to our cloud, various AI algorithms are applied immediately. So you'd be surprised, but even though we're dealing mostly with internal view videos like the ones shown here, there's still instances where the camera that's meant to be going inside the patient is outside of the body for a few moments, usually at the beginning or end of a surgery, but not always. So we have a kind of a stripped down, streamlined version of the de-identification algorithm that is also applied to these videos. But we can arbitrarily link together a series of other AI models that are relevant to the users of this system after that. One of those models is technical skill assessment, which I kind of alluded to before. So this is fairly straightforward. We use state-of-the-art neural networks to either segment or get statistics as to the positions and motions of surgical instruments in the field. And then we've actually collected a couple of hundred statistics, and we use those statistics and a bit of advanced modeling to assess surgeons in a variety of categories. And these include things like, their bimanual coordination, how respectful they are to tissue, how precise they are in their movements, and so on. And the important thing I want to mention here briefly is that all of this is really, bottom-up driven from the data. Alternatives to this exist. There's a system called OSATs. I'm not sure if you can see this, but we've kind of related our work against OSATs, which is one of the standards. But the difference between OSATs and what we can do is that, like, this top-down approach of OSATs is very sensitive to like inter-rater differences, and the results are subsequently almost useless. So this weird paradox in terms of technical skill assessment, where on average, raters will, with very tight variance, almost always rate technical skill across a variety of categories as like a 3 out of 5, which is like good, not great, or maybe a 4 out of 5. So the variance is pretty tight. You very rarely see 5s or 2s or 1s. So it's kind of useless in that respect because you can't really tell very much. Everybody gets a 3 or a 4. So what use is this evaluation? But the paradox comes in the sense that if you have two individuals looking at the same video and applying these subscales on a scale of 1 to 5, there's still a lot of inter-rater disagreement. So people will give 3s and 4s interchangeably. And if you're looking at reliability metrics that are just looking at like nominal differences, the inter-rater reliability will be essentially garbage, essentially. So what we want to do with these sorts of AI and data-driven approaches is to get away with the old-fashioned pen and paper based methods that were devised by committee and really let the data tell us, this is actually the features that matter when we're evaluating technical skill. Our intuition, from top-down approaches really isn't sufficient to this task. So anyway, technical skill assessment is one of the AI models that we're actually deploying now to customers around the world. This is a screenshot of the Black Box Explorer. So one thing I want to note is that there's a big black screen and an X here because of the security I mentioned and the high-grade like DRM. We can't take screenshots or screen captures of our portal into the library. So everything is completely, it's impossible to do that sort of thing for security's sake. The second thing I want to note is that the OR Vision is what we call the AI-based technical skill assessment. And we're focusing on 3 different methods of assessment: bimanual coordination, fine motor control, instrument motion. And from the very beginning, baked into the model is that we wanted this model to be explainable. This is extremely important in clinical applications of AI. It was mentioned in great detail in the talk just previous to this one. So what we're doing, for example, is giving scores for bimanual coordination, not just once for a 2-hour surgery, but in very small increments, arbitrarily small. Usually we give scores like on 2-minute intervals, so you can see if someone's bimanual coordination, for example, changes over time, and then you can zoom in on regions where the AI model found the data to be relevant to that. So I'm super excited. I've, on a personal note, been very interested in explainable AI in healthcare for a long time, and the fact that we're actually deploying this in production is just a dream come true for me. Now, I mentioned we can add a bunch of other assessment or AI models after the fact. So one of them is adverse event detection. This is kind of an incomplete high-level sketch of our model that we use for adverse event detection. These can be things like 3D CNNs or UNets. Not shown here is models that we're open sourcing that allow you to kind of stabilize the video, because it's also not only when you're zooming into the surgical scene, there's a lot of jitter and motion in the camera, which can affect processing. So we've developed this camera stabilization approach, which has actually improved our metrics by a considerable amount. What these graphs showed here at the bottom is like the ground truth annotations of blood and bleeding in blue. And burning and thermal injuries. Occasionally, instruments actually do burn the tissue on purpose in order to separate them, but sometimes it results in an adverse event, an injury, and we want to be able to detect those. So this example shows how accurate kind of qualitatively we are, and quantitatively we're state-of-the-art in detecting blood, and we're also state-of-the-art in detecting burns. That's because we're the only ones who are currently doing it. So, I mean, if ever you've seen a talk of mine, I usually end with this quote from Marshall McLuhan, that first we shape our tools and thereafter our tools shape us. So also a big motivator for us is not just to build the tools themselves, which I think we've made a lot of progress on, but now we have to think about how these tools are actually going to be applied in practice. So what feedback do we get from the tools once users are actually using them? Or in other words, how do we actually qualify the changes these tools themselves make in the world? And to answer that, we actually have to talk about ethics. And we tried to answer parts of this in a book chapter that was published recently in Artificial Intelligence in Surgery by myself and a great PhD student, Rudzicz. It's also open. You can get it in our archive. If you see a video, you should be able to just QR code into this chapter here. Very high level, we touch on a couple of topics, one of which is that, what is the discussion of ethics in a biomedical context? And there's many definitions. One of them provided by Wall et al., who studies bioethics and surgery specifically, is that ethics is usually at a high level a discussion about choice. There's an agent that has to choose between at least two options that are mutually exclusive and have varying amounts of right and wrong in each of them. And neither of them can be perceived as completely right or wrong. So, when we're talking about ethics generally, we're usually talking about choice. And I find that interesting because at their core, our AI systems are also designed to make choices, usually through this nominal categorization. And this is a tangent. This is becoming not exactly an ethical aspect, but, we're observing situations where, the measure of correctness for our models is determined by human judgments. But if we're going into, increasingly critical scenarios or scenarios in which our signals are subtle, our human judges are becoming less reliable, and then there's a whole bunch of questions, technical and non-technical, about how we deal with that situation. But in the vast field of biomedical ethics and surgery, there's, we have a choice when we're actually, trying to detect adverse events or what someone's technical assessment should be. But there's also a choice of which ethical standards we apply to a particular situation. So the prima facie duty theory is very common. This is usually behind the scenes in research ethics boards applications. Alternatively, Little defined these 5 moral pillars, which is interesting. It's ethical decisions more specific to surgical experience. Rather than actually applying broad principles top-down, Wall outlined this root cause analysis of ethical dilemmas. We ask ourselves questions about a surgical scenario in order to elucidate our understanding of ethical considerations for the particular surgery. My point I want to make here is that there's a variety of alternative booklets or standards or approaches to how to make decisions ethically that are devised top-down. But just like kind of the methods we use to generate gold standard labels, top-down, those aren't always appropriate. And surgery in particular often forces surgeons to make decisions on the spot based on unique contextual intricacies which have never been seen before. And they're not normally captured in these kind of if-then-else decision trees or committee-driven approval guidelines. That's not to say that these committee-driven top-down committee guidelines for ethical standards are not useful. It's incredibly useful to have those principles, but surgical ethics in particular is very pragmatic. So it's a bit unique in that standard. And I think if we're going to introduce technology into the operating room with sometimes unknown effects, surgical AI for surgery is also going to have to be dealt with pragmatically when talking about ethics. And our approach has been that explainability will be at the heart of making ethical decisions. It's going to be very difficult to make these pragmatic ethical decisions unless we really have an understanding of what's going on. I'm not going to talk very much about this. The almost exact same points were made in the previous session about why we want machine learning to be explainable. We want to audit the system. We want to make sure it generalizes. We want to trust the system. I also want to add that we want to, sometimes we need the machine learning to be explainable. There's lots of precedent for the regulatory approval processes for Class 1 and Class 2 medical devices in the United States and soon in Canada to have controls related to explainability if your system's going to be approved as a medical device. Across the pond, GDPR has some language in their recitals about the right to explanation. So whether or not, there's an article that came out, I think today or this week in Science that raises some questions about explainable AI in healthcare. So I'd advise you to check it out. I think it's Boris Balic is the first author. But regardless, there is precedent suggesting that we're going to need our AI to be explainable. And we have a paper in JAMA Surgery in which we study a system meant to offer safe interoperative decision support. And the real question here is, not just how does explainable AI work under the hood in order to make explanations that are themselves robust, but now we also have the human factor. How do we, if we're dealing with, real-time decisions in windows of those 1 or 2 minutes, how can we, if we're going to predict something like an adverse event 2 minutes in advance, but we still have the risk of false positives, how do we warn members of the team without providing those distractions that I very briefly mentioned earlier on can actually be highly problematic. So just to wrap up, I think I'm just over time. I'm absolutely thrilled. This is a dream come true that we're actually starting to deploy AI, not just as a background for the papers which we're writing, but actually to our customers. So this has been a goal of our team for a very long time. So actually be able to deploy our de-identification algorithms, our technical skill assessment algorithms, adverse events, and some others, which I would be able to tell you about potentially in a few months. It's going out the door now. So it's incredibly exciting and only a little bit nerve-wracking. Within this context, there's a great pull for AI and data-driven tools to improve efficiency in healthcare and in particular safety in healthcare. But if we're going to try to improve safety in healthcare, if we're going to actually try to save lives in healthcare using these tools, we need to make sure those tools are actually safe themselves. And part of that is going to be better methods of explaining and understanding those systems, but increasingly, not only will we'll have technical challenges to deal with going forward, but now those technical challenges are going to live alongside ethical challenges. So now we're no longer just going to have technologists and clinicians in the room to analyze these systems, but also members from the social sciences as well, which is also incredibly exciting to me. So it's been a very high-level overview of some of the technologies we're deploying currently, but I thank you very much for your attention.
Thank you, Frank, for the interesting talk. Now let's take the questions. Some of our audiences were curious if surgeons are receptive to the idea that their performance is being monitoring during surgery and that an AI is assisting their performance.
That's a great question. And it's really hard to answer that kind of question one way or the other because surgeons aren't all alike, despite what the evidence might sometimes suggest. Some surgeons are incredibly interested by all of this. They say this is amazing, and they actually come to us, the technologists, saying these methods we've been using previously to assess for technical performance or adverse events or the variety of other technical outcomes they care about, they're just useless. For example, the surgical safety checklist is a WHO standard that surgeons are supposed to go through at the beginning of a surgery. It's basically a checklist they go through and just check it off, as the name suggests. And if they do it correctly, and then there's a tremendous amount of benefit that's potentially achievable. But the problem is people don't do it well. So if you're not actually looking over the shoulder of the person administering the checklist, they're just going to kind of, try to get it over with and do a very haphazard job. And there's actually a study in Ontario that shows that the results of doing the safety checklist this way, you might as well not have done it in the first place. And similarly, they told us that technical skill is something that the old methods can't measure reliably. It's just the statistics, if you can call them that, are pretty much useless. Now, I don't want to kind of, I'm always hesitant to sound like machine learning is a silver bullet that's going to solve all of your problems. But in this case, I think it's actually potentially very beneficial. And on one hand, there's something called the Hawthorne effect you might have heard of. If people know they're being watched, they're going to behave better. But this is usually in small doses, right? So if we're looking at people being monitored constantly by these systems and having their data recorded somewhere, that's another set of questions. So I'm going to try to wrap up the question rapidly, but it's an interesting one. Yeah, there was also hesitance from some surgeons. They didn't want the idea that all of their behavior, any mistakes they might make, any reluctance they might show or change in their behavior, they don't want that to be part of the record. So it hasn't been before, and they're worried about their professional status. Now, we've mostly dealt with this. So the CMPA is one of our funders, and they've been very careful and to help us to make sure that there's no personally linked information. So the individual might have access to their personal data, but no one else would, unless they provide consent for that. So really, it's about the individual monitoring their own progress, identifying where they themselves have faltered, and then make modifications themselves. At a global scale, we normally just provide aggregate statistics. So we're very careful to kind of bring in the human element to this, and also the legal element. So I'm not a lawyer. There's a whole group of people that are making sure that we're abiding by privacy standards when we're looking at an individual's records. So we're pretty careful about that.
Yeah, great, thank you. And I think the de-identification algorithm and model that you've mentioned play an important role in this to maybe surgeons feel better. And now let's jump into more technical questions. We have a question, a participant asking, do you use the same machine learning model for technical skill level for different hospitals or clients, or do you train multiple skill rating machine learning model per center's data?
It's also a very good question. So some of this stuff, I mean, like I'm under the conflict of interest thing, so I won't be able to tell you absolutely everything about what our workflow is behind the scenes. But what I can say is that, I mean, yeah, sometimes a partner might say, we really want OSATs. So OSATs is a standard, and we want you to make predictions of OSATs. Not really shown when I showed the Black Box Explorer is that, we have a platform where, we can either have humans annotate according to OSATs at our site or on the partner's site, and that's all supported. We also want to be able to support, a site might say, we have our own in-house mechanism that we use, so we'd have to think about making something bespoke for them. But generally, to answer the first part of the question, is that we want OR vision. So our approach to assessing technical skill in this data-driven approach to be more or less universal. So the fundamentals of the modeling and what it is we're trying to model is something we want to be more or less universal across sites. Now, that being said, the second part of the question is that there's, of course, a lot of variation. There's variation between the age of the individual, like not the age of the seniority. Like there's a difference between a senior staff and a junior resident actually doing a surgery in terms of technical skill. There's differences in terms of the surgery itself. Different procedures have different steps, which are differently difficult. Sometimes there's specifics of that individual. So like the individual on the table can also provide a very important covariate. There's all kinds of, and then the site and the recording equipment, if you're using this kind of camera or that kind of camera. We're actually looking into like more rural implementations of this, not in like Toronto, Boston, or New York, but in more remote categories. So we were trying to build in, even though we want the model to be more or less universal, and the methods they track to be universal, we're also trying to be sensitive to the covariates that can change the behavior. I think that's an important thing that we can do with this data-driven approach that tools like GoSets can't really accomplish.
Yeah, and a following-up question could be, for example, as you mentioned, different covariates maybe, although you've trying to keep the central model universal, but as you mentioned, we might see, for example, a data drift or something like that. And do you retrain your models and redeploy? If so, what are the validation procedures to make sure the updated model weights does not affect the safety and effectiveness of the model in that regard?
Yeah, I think I'm going to have to I guess plead the fifth is the right term for this. The behind the scenes of how we retrain and monitor our models is sort of a bit of a secret sauce. But I can say that, yeah, we do automate the monitoring of models, like the distributional shift and generalizability are two very important factors for us. So whenever we deploy to a new site, that's built into our workflow. Yeah, and we also, I mean, kind of implicit in what I was talking about earlier was that, we don't necessarily always have the AI working on its own. We also have a team of clinicians that can help clean up any errors that the AI might have produced, or just kind of do a sanity check after the fact. So we have a couple of layers of security to make sure that the models are behaving as intended as they're deployed for long periods of time.
Great, thank you. I'm sure that this has answered our attendees' question. And back to the privacy concerns, I see that we have a question. I'm not sure if you want to answer this question or not, but the question is, has evidence from your system been used in a medical legal case?
Medical legal, I don't think so. I don't think it's ever been brought before the courts before, but evidence from our systems have been used variously at our various sites in terms of changing clinical practice. So that was kind of, for me anyway, one of and I guess the team was one of the most important things we wanted to see happen, is that we wanted to see that we're not just producing systems that are going to just produce tables of results, but actually kind of affect how people behave. And there's various instances. I mean, the different deployments have been sometimes bespoke a little bit. So I haven't been able to talk about all of the different things we've done, but in some cases, we've been able to identify with our partners, behavior that was either really good or that could use some correction, and then to either promote that behavior or carefully correct the behavior. So we're actually seeing real world change, which is very gratifying.
Thank you. Thank you, Frank, for taking the time to answering all the questions. And it was a very interesting talk and subject. And thank you all for all of the audience for attending this talk. And I hope that I can see you in other talks as well. Thank you. Thank you so much.